Section 1 Introduction. We're here to discuss the rise of large language models, LLMs, like GPT and PaLM, which have opened up new possibilities such as programming assistants and universal chatbots. These applications are starting to significantly influence our work and daily lives. Many companies that provide cloud services are in a race to offer these applications as hosted services. However, running these applications is quite costly, as they require a lot of hardware accelerators like GPUs. Recent estimates suggest that processing a request from an LLM can be 10 times more expensive than a traditional keyword query. Given these high costs, it's becoming increasingly important to boost the throughput, and thus reduce the cost per request, of LLM serving systems. At the heart of LLMs is an autoregressive transformer model. This model generates words, one by one, based on the input and the sequence of previously generated output words. For each request, this costly process is repeated until the model produces a termination token. This sequential generation process makes the workload memory-bound, which underutilizes the computational power of GPUs and limits the throughput. We can improve the throughput by processing multiple requests at once, but this requires efficient management of the memory space for each request. Let's take an example of a 13 billion parameter LLM running on an NVIDIA A100 GPU with 40 GB RAM. Around 65% of the memory is allocated for the model weights, which remain static during serving. Nearly 30% of the memory is used to store the dynamic states of the requests. For transformers, these states consist of the key and value tensors associated with the attention mechanism, often referred to as KV cache. This represents the context from earlier tokens to generate new output tokens in sequence. The remaining small percentage of memory is used for other data, including activations, the temporary tensors created when evaluating the LLM. Since the model weights are constant and the activations only occupy a small fraction of the GPU memory, the way the KV cache is managed is crucial in determining the maximum batch size. If managed inefficiently, the KV cache memory can significantly limit the batch size and consequently the throughput of the LLM. We've noticed that existing LLM serving systems struggle to manage the KV cache memory efficiently. This is mainly because they store the KV cache of a request in contiguous memory space, as most deep learning frameworks require tensors to be stored in contiguous memory. However, unlike the tensors in traditional deep learning workloads, the KV cache has unique characteristics. It dynamically grows and shrinks over time as the model generates new tokens, and its lifetime and length are not known in advance. These characteristics make the existing system's approach significantly inefficient in two ways. First, the existing systems suffer from internal and external memory fragmentation. They pre-allocate a contiguous chunk of memory with the request's maximum length, which can result in severe internal fragmentation. Moreover, even if the actual length is known in advance, the pre-allocation is still inefficient. Second, the existing systems cannot exploit the opportunities for memory sharing. LLM services often use advanced decoding algorithms that generate multiple outputs per request. In these scenarios, the request consists of multiple sequences that can partially share their KV cache. However, memory sharing is not possible in the existing systems because the KV cache of the sequences is stored in separate contiguous spaces. To address these limitations, we propose PagedAttention, an attention algorithm inspired by the operating system solution to memory fragmentation and sharing, virtual memory with paging. PagedAttention divides the request's KV cache into blocks, each of which can contain the attention keys and values of a fixed number of tokens. In PagedAttention, the blocks for the KV cache are not necessarily stored in contiguous space. This design alleviates internal fragmentation by using relatively small blocks and allocating them on demand. Moreover, it eliminates external fragmentation as all blocks have the same size. Finally, it enables memory sharing at the granularity of a block, across the different sequences associated with the same request or even across the different requests. In this work, we build vLLM, a high-throughput distributed LLM serving engine on top of PagedAttention that achieves near-zero waste in KV cache memory. vLLM uses block-level memory management and preemptive request scheduling that are co-designed with PagedAttention. vLLM supports popular LLMs such as GPT, Opt, and Llama with varying sizes, including the ones exceeding the memory capacity of a single GPU. Our evaluations on various models and workloads show that vLLM improves the LLM serving throughput by 2 to 4 times compared to the state-of-the-art systems, without affecting the model accuracy at all. The improvements are more pronounced with longer sequences, larger models, and more complex decoding algorithms. In summary, we make the following contributions. We identify the challenges in memory allocation in serving LLMs and quantify their impact on serving performance. We propose PagedAttention, an attention algorithm that operates on KV cache stored in non-contiguous paged memory, which is inspired by the virtual memory and paging in OS. We design and implement vLLM, a distributed LLM serving engine built on top of PagedAttention. We evaluate vLLM on various scenarios and demonstrate that it substantially outperforms the previous state-of-the-art solutions such as Faster Transformer and Orca. Section Summary. Large language models, LLMs, like GPT and PaLM have enabled new applications such as programming assistants and chatbots, but running these applications is expensive due to the need for hardware accelerators. The autoregressive transformer model at the core of LLMs generates words one at a time, making the workload memory-bound and limiting serving throughput. To address this, the authors propose PagedAttention, an attention algorithm inspired by virtual memory with paging, which divides the request's key-value cache into blocks and allows for more efficient memory management and sharing. Their distributed LLM serving engine, vLLM, built on top of PagedAttention, achieves significantly improved throughput without affecting model accuracy. Section 2 Background. Let's delve into the background of our study. We'll be discussing how typical large language models, LLMs, are generated and served, and how scheduling is done at the iteration level during LLM serving. Firstly, we'll talk about transformer-based large language models. Language modeling is all about predicting the likelihood of a sequence of tokens, or words. Because language naturally follows a sequence, we often break down the probability of the entire sequence into the product of conditional probabilities. This is known as autoregressive decomposition. In simpler terms, we're trying to predict the probability of a word given the words that came before it. Transformers have become the go-to architecture for modeling these probabilities on a large scale. The most crucial part of a transformer-based language model is its self-attention layers. For an input sequence, a self-attention layer first applies linear transformations to each position to get the query, key, and value vectors. Then, it calculates the attention score by multiplying the query vector at one position with all the key vectors before it. The output is computed as the weighted average over the value vectors. Apart from this computation, all other components in the transformer model, including the embedding layer, feed-forward layer, layer normalization, residual connection, output logit computation, and the query, key, and value transformation, are all applied independently position-wise. Once trained, LLMs are often used as a conditional generation service, like a completion API or chatbot. A request to an LLM service provides a list of input prompt tokens, and the LLM service generates a list of output tokens according to the previously mentioned probability model. We refer to the combination of the prompt and output lists as a sequence. Due to the decomposition, the LLM can only sample and generate new tokens one by one, and the generation process of each new token depends on all the previous tokens in that sequence, specifically their key and value vectors. In this sequential generation process, the key and value vectors of existing tokens are often stored for generating future tokens, known as KV cache. Note that the KV cache of one token depends on all its previous tokens. This means that the KV cache of the same token appearing at different positions in a sequence will be different. Given a request prompt, the generation computation in the LLM service can be broken down into two phases, the prompt phase and the autoregressive generation phase. The prompt phase takes the whole user prompt as input and computes the probability of the first new token. During this process, it also generates the key vectors and value vectors. Since prompt tokens are all known, the computation of the prompt phase can be parallelized using matrix-matrix multiplication operations. Therefore, this phase can efficiently use the parallelism inherent in GPUs. The autoregressive generation phase generates the remaining new tokens sequentially. At each step, the model takes one token as input and computes the probability of the next token with the key vectors and value vectors. Note that the key and value vectors at previous positions are stored at previous iterations. Only the new key and value vector are computed at this iteration. This phase completes either when the sequence reaches a maximum length, specified by users or limited by LLMs, or when an end-of-sequence token is emitted. The computation at different iterations cannot be parallelized due to the data dependency and often uses matrix vector multiplication, which is less efficient. As a result, this phase severely underutilizes GPU computation and becomes memory-bound, being responsible for most portion of the latency of a single request. Section Summary. Transformer-based large language models, LLMs, are commonly used for language modeling tasks, where the probability of a sequence of tokens is modeled by factorizing it into conditional probabilities. LLMs generate new tokens sequentially, with each token's generation depending on all previous tokens. The generation process involves a prompt phase, which can be parallelized efficiently, and an autoregressive generation phase, which is less efficient and memory-bound. Section 2.3 Batching Techniques for LLMs. We're going to discuss two main topics: batching techniques for large language models, LLMs, and the memory challenges that come with serving these models. First, let's talk about batching techniques. When we're working with LLMs, we can make our computing more efficient by grouping multiple requests together. This is because all the requests use the same model weights, so the cost of moving these weights around is spread across all the requests in a batch. This becomes especially beneficial when we have a large batch size, as the computational overhead can outweigh the cost of moving the weights. However, batching isn't as simple as it might seem. There are two main challenges. Firstly, requests can arrive at different times. If we batch requests naively, we might end up making earlier requests wait for later ones, or we might delay incoming requests until the earlier ones are done. This can lead to significant delays. Secondly, requests can have very different input and output lengths. If we just batch requests without considering this, we might end up wasting computational resources and memory by padding the inputs and outputs to make them the same length. To overcome these challenges, we can use fine-grained batching mechanisms, like cellular batching and iteration-level scheduling. Unlike traditional methods, these techniques work at the iteration level. After each iteration, we remove completed requests from the batch and add new ones. This means that a new request only has to wait for one iteration, not for the whole batch to finish. Plus, with special GPU kernels, we can avoid the need to pad inputs and outputs. By reducing delays and inefficiencies, these fine-grained batching mechanisms can significantly increase the throughput of LLM serving. Now, let's move on to the memory challenges. Even though fine-grained batching helps us use our computing resources more efficiently, the number of requests we can batch together is still limited by the memory capacity of our GPU, especially the space allocated to store the key value, KV, cache. In other words, our system's throughput is limited by memory. To overcome this memory limitation, we need to address several challenges. Firstly, the KV cache size grows quickly with the number of requests. For example, for a model with 13 billion parameters, the KV cache for a single token requires 800 kilobytes of space. This is calculated as 2, for the key and value vectors, times 5120, the hidden state size, times 40, the number of layers, times 2, bytes per FP16. Since this model can generate sequences of up to 2048 tokens, storing the KV cache for one request can require as much as 1.6 gigabytes of memory. Given that GPUs typically have memory capacities in the tens of GBs, even if we allocated all available memory to the KV cache, we could only accommodate a few tens of requests. Secondly, LLM services offer a range of decoding algorithms, each with different implications for memory management. For example, when users request multiple random samples from a single input prompt, we can share the KV cache of the prompt part to minimize memory usage. However, the KV cache during the autoregressive generation phase should remain unshared due to the different sample results and their dependence on context and position. The extent of KV cache sharing depends on the specific decoding algorithm used. Thirdly, the requests to an LLM service can vary greatly in their input and output lengths. This means that our memory management system needs to be able to handle a wide range of prompt lengths. As the output length of a request grows during decoding, the memory required for its KV cache also expands, which could exhaust the available memory for incoming requests or ongoing generation for existing prompts. In existing systems, most operators in current deep learning frameworks require tensors to be stored in contiguous memory, so the KV cache of one request is also stored as a contiguous tensor across the different positions. Because the output lengths from the LLM are unpredictable, these systems statically allocate a chunk of memory for a request based on the request's maximum possible sequence length, regardless of the actual input or eventual output length of the request. This approach has three main sources of memory waste: reserved slots for future tokens, internal fragmentation due to over-provisioning for potential maximum sequence lengths, and external fragmentation from the memory allocator. Although compaction has been proposed as a potential solution to fragmentation, it's not practical in a performance-sensitive LLM serving system due to the large size of the KV cache. Even with compaction, the pre-allocated chunk space for each request prevents memory sharing specific to decoding algorithms in existing memory management systems. Section Summary. Batching techniques for language model, LLM, serving can improve compute utilization by amortizing the overhead of moving weights across multiple requests. However, naive batching strategies can lead to significant queuing delays and waste GPU computation and memory. Fine-grained batching mechanisms, such as cellular batching and iteration-level scheduling, address these challenges by operating at the iteration level and eliminating the need for padding inputs and outputs, thereby increasing LLM serving throughput. Additionally, memory management in LLM serving systems faces challenges such as large KV cache sizes, complex decoding algorithms, and scheduling for unknown input and output lengths. Existing systems statically allocate memory based on maximum possible sequence lengths, resulting in memory waste from reserved slots, internal fragmentation, and external fragmentation. Section 4 Method. In this study, we've created a novel attention algorithm called PagedAttention and a language model serving engine known as vLLM to address the issues we've previously discussed. The vLLM structure is depicted in a figure. It uses a centralized scheduler to manage the execution of distributed GPU workers. The KV cache manager, powered by PagedAttention, effectively handles the KV cache in a paged manner. More specifically, the KV cache manager controls the physical KV cache memory on the GPU workers based on instructions from the centralized scheduler. We'll first explain the PagedAttention algorithm, then we'll discuss the design of the KV cache manager and how it supports PagedAttention. We'll also show how this design aids in efficient memory management for various decoding methods and accommodates variable length input and output sequences. Lastly, we'll demonstrate how the vLLM system design operates in a distributed setting. To tackle the memory challenges, we've developed PagedAttention, an attention algorithm that draws inspiration from the concept of paging in operating systems. Unlike traditional attention algorithms, PagedAttention allows for the storage of continuous keys and values in non-contiguous memory space. It does this by dividing the KV cache of each sequence into KV blocks, each containing the key and value vectors for a fixed number of tokens. In the transformer model, each token has a set of key and value vectors across layers and attention heads within a layer. All the key and value vectors can be managed together within a single KV block, or the key and value vectors at different heads and layers can each have a separate block and be managed in separate block tables. We chose the latter design for easier implementation. We denote the size of the KV block as B. The key block K_J and value block V_J are defined as the key and value vectors for a fixed number of tokens. The attention computation can be transformed into a block-wise computation. Here, A_IJ is the row vector of attention score on the JTHKV block. During the attention computation, the PagedAttention kernel identifies and fetches different KV blocks separately. For example, the key and value vectors are spread across 3 blocks, and these blocks are not contiguous on the physical memory. At each step, the kernel multiplies the query vector of the query token and the key vectors in a block to compute the attention score, and later multiplies this score with the value vectors in a block to derive the final attention output. In essence, the PagedAttention algorithm allows the KV blocks to be stored in non-contiguous physical memory, which enables more flexible paged memory management in vLLM. The vLLM's memory manager operates similarly to the virtual memory in operating systems. The OS partitions memory into fixed-sized pages and maps user programs' logical pages to physical pages. Contiguous logical pages can correspond to non-contiguous physical memory pages, allowing user programs to access memory as though it were contiguous. Moreover, physical memory space doesn't need to be fully reserved in advance, enabling the OS to dynamically allocate physical pages as needed. vLLM uses these ideas to manage the KV cache in a language model service. With PagedAttention, we organize the KV cache as fixed-size KV blocks, similar to pages in virtual memory. A request's KV cache is represented as a series of logical KV blocks, filled from left to right as new tokens and their KV cache are generated. The last KV block's unfilled positions are reserved for future generations. On GPU workers, a block engine allocates a contiguous chunk of GPU DRAM and divides it into physical KV blocks. The KV block manager also maintains block tables, the mapping between logical and physical KV blocks of each request. Each block table entry records the corresponding physical blocks of a logical block and the number of filled positions. This separation of logical and physical KV blocks allows vLLM to dynamically grow the KV cache memory without reserving it for all positions in advance, which eliminates most memory waste in existing systems. Section Summary. In this section, the authors introduce a new attention algorithm called PagedAttention, which allows for storing continuous keys and values in non-contiguous memory space. This algorithm partitions the KV cache into blocks and performs block-wise computations to derive the attention output. Additionally, the authors propose a KV cache manager inspired by virtual memory, which dynamically allocates physical memory pages as needed, allowing for flexible memory management in the LLM service. Section 4.3 Decoding with PagedAttention and vLLM. In this section, we'll explain how the vLLM system uses PagedAttention and manages memory during the decoding process of a single input sequence. Firstly, vLLM, like an operating system's virtual memory, doesn't need to reserve memory for the longest possible generated sequence from the start. Instead, it only reserves the necessary key value, KV, blocks to accommodate the KV cache created during prompt computation. For example, if the prompt has 7 tokens, vLLM maps the first 2 logical KV blocks to 2 physical KV blocks. It then generates the KV cache of the prompts and the first output token using a standard self-attention algorithm. The KV cache of the first 4 tokens is stored in logical block 0 and the next 3 tokens in logical block 1. The remaining slot is reserved for the next autoregressive generation phase. In the first autoregressive decoding step, vLLM creates a new token using the PagedAttention algorithm on physical blocks. Since there's still one slot available in the last logical block, the newly generated KV cache is stored there, and the block table's record is updated. At the second decoding step, as the last logical block is full, vLLM stores the newly generated KV cache in a new logical block. It allocates a new physical block for it and stores this mapping in the block table. For each decoding iteration, vLLM first selects a set of candidate sequences for batching, and allocates the physical blocks for the newly required logical blocks. Then, it concatenates all the input tokens of the current iteration as one sequence and feeds it into the LLM. During LLM's computation, vLLM uses the PagedAttention kernel to access the previous KV cache stored in the form of logical KV blocks and saves the newly generated KV cache into the physical KV blocks. Storing multiple tokens within a KV block enables the PagedAttention kernel to process the KV cache across more positions in parallel, thus increasing the hardware utilization and reducing latency. However, a larger block size also increases memory fragmentation. vLLM dynamically assigns new physical blocks to logical blocks as more tokens and their KV cache are generated. As all the blocks are filled from left to right and a new physical block is only allocated when all previous blocks are full, vLLM limits all the memory wastes for a request within one block, so it can effectively utilize all the memory. This allows more requests to fit into memory for batching, hence improving the throughput. Once a request finishes its generation, its KV blocks can be freed to store the KV cache of other requests. We also show an example of vLLM managing the memory for 2 sequences. The logical blocks of the 2 sequences are mapped to different physical blocks within the space reserved by the block engine in GPU workers. The neighboring logical blocks of both sequences do not need to be contiguous in physical GPU memory, and the space of physical blocks can be effectively utilized by both sequences. vLLM can also handle more complex decoding scenarios that exhibit complex accessing patterns and more opportunities for memory sharing. For example, in LLM-based program assistance, an LLM generates multiple sampled outputs for a single input prompt. Users can choose a favorite output from various candidates. In this case, vLLM can realize this sharing easily and save memory. In beam search, which is widely used to decode the most probable output sequence from an LLM, vLLM manages the KV blocks for a beam search example. It frees all physical blocks whose reference counts reach 0 and allocates new physical blocks to store the new KV cache from the new candidates. In the case of shared prefix, where many user prompts share a prefix, the LLM service provider can store the KV cache of the prefix in advance to reduce the redundant computation spent on the prefix. In vLLM, this can be conveniently achieved by reserving a set of physical blocks for a set of predefined shared prefixes by the LLM service provider. Finally, vLLM facilitates the simultaneous processing of requests with different decoding preferences, which existing systems cannot efficiently do. This is because vLLM conceals the complex memory sharing between different sequences via a common mapping layer that translates logical blocks to physical blocks. The LLM and its execution kernel only see a list of physical block IDs for each sequence and do not need to handle sharing patterns across sequences. Compared to existing systems, this approach broadens the batching opportunities for requests with different sampling requirements, ultimately increasing the system's overall throughput. Section Summary. The vLLM model uses paged attention and a paged memory management system to efficiently execute the decoding process. It dynamically assigns physical blocks to logical blocks, allowing for effective memory utilization and reducing memory waste. Additionally, vLLM supports various decoding scenarios, such as parallel sampling and beam search, by enabling memory sharing and implementing a copy-on-write mechanism. This approach improves memory usage and reduces computational overhead, resulting in increased throughput for the system. Section 4.5 Scheduling and Preemption. In Section 4.5, we discuss the process of scheduling and preemption in our system, vLLM. When the number of requests exceeds the system's capacity, vLLM must prioritize certain requests. We use a first-come, first-served policy to ensure fairness and prevent any request from being left out indefinitely. When vLLM needs to interrupt requests, it does so in reverse order, starting with the most recent requests. This is a unique challenge for LLM services because the length of the input prompts can vary greatly, and the length of the resulting outputs is unpredictable. As the number of requests and their outputs increase, vLLM may run out of storage space on the GPU for the newly generated key value cache. In this situation, vLLM must answer two key questions. Which blocks should be removed, and how can these removed blocks be recovered if needed again? We use a heuristic approach to predict which block will be accessed furthest in the future and remove that block. We also implement an all-or-nothing policy, meaning we either remove all or none of the blocks of a sequence. To recover a removed block, we consider two techniques, swapping and recomputation. Swapping involves copying the removed blocks to the CPU memory. When vLLM runs out of free blocks for new tokens, it selects a set of sequences to remove and transfers their key value cache to the CPU. Once a sequence is interrupted and its blocks are removed, vLLM stops accepting new requests until all interrupted sequences are completed. Recomputation, on the other hand, involves recalculating the key value cache when the interrupted sequences are rescheduled. The time taken for recomputation can be significantly less than the original time, as the tokens generated at decoding can be combined with the original user prompt as a new prompt. In Section 4.6, we discuss distributed execution. Many LLMs have parameter sizes that exceed the capacity of a single GPU. Therefore, it's necessary to divide them across multiple GPUs and execute them in a model parallel fashion. This requires a memory manager capable of handling distributed memory. vLLM is effective in distributed settings by supporting the widely used Megatron LM-style tensor model parallelism strategy on transformers. This strategy follows a single program multiple data execution schedule, where the linear layers are divided to perform block-wise matrix multiplication, and the GPUs constantly synchronize intermediate results. Even with model parallel execution, each model shard still processes the same set of input tokens, thus requiring the key value cache for the same positions. Therefore, vLLM features a single key value cache manager within the centralized scheduler. Different GPU workers share the manager, as well as the mapping from logical blocks to physical blocks. This common mapping allows GPU workers to execute the model with the physical blocks provided by the scheduler for each input request. In each step, the scheduler first prepares the message with input token IDs for each request in the batch, as well as the block table for each request. Then, the scheduler broadcasts this control message to the GPU workers. During execution, the GPU workers synchronize the intermediate results without the coordination of the scheduler. In the end, the GPU workers send the sampled tokens of this iteration back to the scheduler. In summary, GPU workers do not need to synchronize on memory management, as they only need to receive all the memory management information at the beginning of each decoding iteration along with the step inputs. Section Summary. In the context of vLLM, scheduling and preemption are crucial when the request traffic exceeds the system's capacity. vLLM adopts a first-come, first-serve (FCFS) scheduling policy to ensure fairness and prevent starvation. When preemption is necessary, vLLM prioritizes the earliest arrived requests and evicts blocks using an all-or-nothing eviction policy, with two techniques for recovery: swapping blocks to CPU memory or recomputing the KV cache. In distributed execution, vLLM supports model parallelism and features a centralized scheduler with a single KV cache manager shared among GPU workers. Section 5 Implementation. We've developed a system called vLLM, which is a complete serving system that includes a fast API frontend and a GPU-based inference engine. This system is designed to extend the OpenAI API interface, allowing users to customize parameters for each request, such as the maximum sequence length and the beam width k. The vLLM engine is built using Python and C++ CUDA code. We've developed control-related components in Python, while custom CUDA kernels are used for key operations. We've also implemented popular language models like GPT, Opt, and Llama using PyTorch and transformers. We've optimized the system at the kernel level, as the PagedAttention operation introduces memory access patterns that aren't efficiently supported by existing systems. We've developed several GPU kernels to optimize this. For instance, we've fused reshape and block write operations into a single kernel to minimize kernel launch overheads. We've also adapted the attention kernel to read KV cache according to the block table and perform attention operations on the fly. We've also implemented a kernel that batches the copy operations for different blocks into a single kernel launch to mitigate overhead. vLLM supports various decoding algorithms using three key methods: fork, append, and free. The fork method creates a new sequence from an existing one, the append method adds a new token to the sequence, and the free method deletes the sequence. This strategy is applied in parallel sampling, beam search, and prefix sharing by vLLM. We've evaluated the performance of vLLM under a variety of workloads using opt models with 13B, 66B, and 175B parameters and Llama with 13B parameters. We've used A2 instances with NVIDIA A100 GPS on Google Cloud Platform for all of our experiments. We've synthesized workloads based on shared GPT and Alpaca datasets, which contain input and output texts of real language model services. We've compared vLLM with two baselines, Faster Transformer and Orca. Faster Transformer is a distributed inference engine optimized for latency, while Orca is a state-of-the-art language model serving system optimized for throughput. We've implemented our own version of Orca as it's not publicly available. We've focused on serving throughput as the key metric. We've measured normalized latency of the systems using workloads with different request rates. A high-throughput serving system should maintain low normalized latency against high request rates. For most experiments, we've evaluated the systems with 1-hour traces. However, for the Opt 175B model, we've used 15-minute traces due to cost limitations. Section Summary. The implementation of vLLM consists of a fast API frontend and a GPU-based inference engine written in Python and C++, CUDA. Kernel-level optimizations are developed to improve memory access patterns and support variable sequence lengths. vLLM also supports various decoding algorithms using methods such as fork, append, and free. The performance of vLLM is evaluated using opt models with different parameters and workloads synthesized from real LLM services. The serving throughput, measured by normalized latency, is the key metric for evaluation. Section 6.2 Basic Sampling. In this section, we'll discuss the performance of our model, vLLM, using basic sampling on 3 different models and 2 datasets. We observed that as the request rate increases, the latency initially rises slowly but then suddenly spikes. This is because when the request rate exceeds the system's capacity, the queue length and latency continue to grow indefinitely. On the shared GPT dataset, vLLM can handle 1.7 to 2.7 times more requests than Orca, Oracle, and 2.7 to 8 times more than Orca, Max, while keeping latencies similar. This is due to vLLM's PagedAttention feature, which efficiently manages memory usage and allows for more requests to be batched than Orca. For instance, for OPT13B, vLLM processes 2.2 times more requests simultaneously than Orca, Oracle, and 4.3 times more than Orca, Max. Compared to Faster Transformer, vLLM can handle up to 22 times more requests, as Faster Transformer does not use a fine-grained scheduling mechanism and manages memory inefficiently like Orca, Max. We also tested vLLM on the Alpaca dataset, which showed similar trends to the shared GPT dataset. However, there was one exception where vLLM's advantage over Orca, Oracle, and Orca, POW2, was less noticeable. This was because the model and server configuration for OPT175B allowed for a large GPU memory space to store KV cache, while the Alpaca dataset has short sequences. As a result, the performance of the systems became compute-bound rather than memory-bound. Next, we evaluated the effectiveness of memory sharing in PagedAttention with 2 popular sampling methods: parallel sampling and beam search. In parallel sampling, all parallel sequences in a request can share the KV cache for the prompt. With a larger number of sequences to sample, vLLM brings more improvement over the Orca baselines. For beam search, since it allows for more sharing, vLLM shows even greater performance benefits. The improvement of vLLM over Orca, Oracle, on OPT13B and the Alpaca dataset goes from 1.3 times in basic sampling to 2.3 times in beam search with a width of 6. We also measured the amount of memory saving, which was calculated by the number of blocks we saved by sharing divided by the total number of blocks without sharing. We observed 6.1% to 9.8% memory saving on parallel sampling and 37.6% to 55.2% on beam search. We also explored the effectiveness of vLLM when a prefix is shared among different input prompts. For this, we used the Llama 13B model, which is multilingual, and the WMT16 English to German translation dataset. We found that vLLM achieves 1.67 times higher throughput than Orca, Oracle, when the one-shot prefix is shared. Furthermore, when more examples are shared, vLLM achieves 3.58 times higher throughput than Orca, Oracle. Finally, we implemented a chatbot, one of the most important applications of LLMs. We found that vLLM can handle 2 times more request rates compared to the 3 Orca baselines. This is because vLLM can effectively handle long prompts, as PagedAttention resolves the problem of memory fragmentation and reservation. Section Summary. The performance of vLLM with basic sampling is evaluated on different models and datasets. It is observed that vLLM can handle higher request rates compared to Orca and Faster Transformer, while maintaining similar latencies, due to its efficient memory management. The effectiveness of memory sharing in PagedAttention is also demonstrated with parallel sampling and beam search, showing significant performance benefits. Additionally, vLLM proves to be effective in scenarios where a prefix is shared among different input prompts, achieving higher throughput. In the context of chatbot applications, vLLM can sustain higher request rates compared to Orca baselines, especially when dealing with long prompts. Section 7 Ablation Studies. In this section, we'll delve into various aspects of our vLLM model and evaluate the design choices we've made through a series of ablation experiments. Firstly, we'll look at the kernel microbenchmark. The dynamic block mapping in our PagedAttention feature impacts the performance of GPU operations that involve the stored KV cache, such as block read, writes, and attention. Compared to existing systems, our GPU kernels require additional overheads for accessing the block table, executing extra branches, and managing variable sequence lengths. This results in a 20 to 26% increase in attention kernel latency compared to the highly optimized faster transformer implementation. However, we believe this overhead is minimal as it only affects the attention operator and not other operators in the model, like linear. Despite this overhead, PagedAttention allows vLLM to significantly outperform faster transformer in overall performance. Next, we'll discuss the impact of block size. The size of the block can greatly affect the performance of vLLM. If the block size is too small, vLLM may not fully utilize the GPU's parallelism for reading and processing KV cache. If the block size is too large, internal fragmentation increases and the likelihood of sharing decreases. We evaluated vLLM's performance with different block sizes using the shared GPT and alpaca traces with basic sampling under fixed request rates. For the shared GPT trace, block sizes from 16 to 128 resulted in the best performance. For the alpaca trace, while block sizes of 16 and 32 worked well, larger block sizes significantly reduced performance as the sequences became shorter than the block sizes. In practice, we found that a block size of 16 is large enough to efficiently use the GPU and small enough to avoid significant internal fragmentation in most workloads. Therefore, vLLM's default block size is set to 16. Lastly, we'll compare recomputation and swapping. vLLM supports both recomputation and swapping as recovery mechanisms. To understand the trade-offs between these two methods, we evaluated their overall performance and micro-benchmarked their overheads. Our results showed that swapping incurs excessive overhead with small block sizes. This is because small block sizes often result in numerous small data transfers between the CPU and GPU, which limits the effective PCIe bandwidth. In contrast, the overhead of recomputation remains constant across different block sizes, as recomputation does not utilize the KV blocks. Therefore, recomputation is more efficient when the block size is small, while swapping is more efficient when the block size is large. However, the recomputation overhead is never more than 20% of swapping's latency. For medium block sizes from 16 to 64, both methods show comparable overall performance.